this is not a statistics class. I've said that a few times. But in our effort to understand how we conduct field sciences, particularly sciences that involve spatial data, it helps to understand just a couple things about how the scientific method works. And the scientific method leans on the conventional tools of inference that we collectively call statistical theory. Now I just want to walk through an example of this. In the previous VoiceThread, I talked about using a static image. I walked through how we calculate the mean and the variance and the standard deviation of a sample. I learned this by doing it. I'm a kinesthetic learner. I find it much easier to understand things if I do them. And so what I'm going to do right now is show you how to calculate the mean and the variance and the standard deviation of a sample. Now the example I'm using here is the 5 trials of ping pong balls in a section of the creek, and you can see the results of that. And the first thing I want to know is, okay, so what's the typical result? I've got these 5 trials. What do they tell me? And they're kind of all over the place. But if I take all of these and add them together, so if I take the sum of this variable x that we've created, which is how many seconds did it take the ping pong ball to float downstream, and divide it by the number of observations I have, n, then I'll have the mean. And when I do that, I'm not quite sure what the sum is, but if I calculate this out, I get a mean of 18. Now, I hope that formula right there doesn't intimidate you, because this is something you do reflexively when you calculate the average of something. You add them all together. That's what that sigma means. Add that column of numbers together. Each of them is an instance that we've calculated, that we've observed, of x. And then we're just dividing by our sample size, which in this case is 5. We've got 5 observations. So that's sort of like the typical case. We're saying that 18 tells us something about the sample. It tells us what the midpoint of it is. Now, if you graph this, you'd see it's actually symmetrical. I kind of winged it. I made these numbers up. Your numbers may vary, and in fact, one thing you might ask is, what if I got a really large number? What if my ping pong ball got stuck for a while and I got 120 minutes, and my distribution is kind of importantly different? That's totally true. We'll talk a little bit about what that means. But for now, what we're saying is this is the midpoint of our observations. But we know just by looking that it doesn't speak for all of our observations. So if we say 18 is sort of, it's the sum of our sample, we're kind of leaving something out. So what we tend to do is say, well, let's talk about the center of our distribution, and then let's measure how far away from the center our observations stray. How much do they vary away from that midpoint? Now, the conventional or the obvious way to do this would be to say, well, what's the average deviation? How far on average are my observations from 18? Well, so I could say, well, how far away is 16 from 18? If I measure that distance, I get -2. So on a number line, 16 is 2 below 18. And I can work that out for all of these. 22 minus 18 is 4. 18 minus 18 is 0. 14 minus 18 is -4. 20 minus 18 is 2. And so now I can say, well, what is the average deviation? On average, how far are my observations away from 18? Well, to calculate the average, I would just add these together and divide by 5. So -2 plus 4 is 2, plus 0 is 2, minus 4 is -2, and plus 2 is 0. So I take 0 and I divide that by 5, and I get an average deviation of 0. That doesn't make any sense. I know that not all of these are exactly 0, so how could it be possible that the average is 0? It's basically saying all of my observations are at the mean. So that number doesn't make any sense. For this reason, in statistics, instead of looking at the mean deviations, how far is each observation from the mean, we look at and so mean deviations using symbols is x minus x bar, where x bar is the mean of x. So I'm saying, how far is each observation of x from the mean of x? Those are mean deviations. So instead of working with mean deviations and saying, what's the average distance of my observations from the mean, which is what we'd be calculating here if we could get something other than 0, if we got something meaningful, we're going to square these deviations. Seems strange, but we take x minus x bar squared. So how far is this observation away from the mean? -2. And then we square that distance, and we do that for each of our observations. And so the squared deviations look like this. Now I can calculate the average squared deviations. First, I need to get the sum. Whoop, that's an ugly sigma. The sum of these mean deviations. So when I add together those squared mean deviations, that just means take this column of numbers, which is my x minus x bar squareds. So each of these squared is x minus x bar squared. Now I'm just adding them all together. So I get 40. That means the sum of these squared deviations is 40. So what's the average squared deviation? That we call the variance. And that's our measure of how variable our sample is. But we don't quite calculate the average. The average would just be taking this and dividing it by n. And in statistics, for a variety of theoretical reasons, we don't do that. Part of it is we want to take into account when we don't have a lot of information. In this case, we only have 5 observations. How reliant can we, or how reliable do we think that sample actually is? So to account for or accommodate our uncertainty, we're going to, instead of dividing by n, we're going to divide by n minus 1. This is a term called degrees of freedom. And when I take 40 and divide it by n minus 1, well, n is my sample size, so I've got 5 observations. N minus 1 is 4. And if I divide 40 by 4, I get 10, I think. This is what we call the variance. The sum of the squared mean deviations divided by the sample size minus 1 is 10. That's the variance of my sample. Now if I take 10, that might be falling off the bottom of the screen, I can't tell yet, but if I take 10, this is a strange number to interpret because it is still based on these squared distances. It's basically the average squared distance from the mean. To make it more meaningful, I can take the square root of this. So I take the square root of 10. Did I mention that I got an F in handwriting in 5th grade? So when I take the square root of 10 over here, possibly off the screen, calculate it on your own, you'll see that the square root is 3.2. That number is the standard deviation. The standard deviation is sort of like the average deviation. On average, how far away are my observations from 18? The standard deviation kind of lets me see that. It allows me to see that the typical observation is somewhere within that distance. Some might be farther, but the farther you get away, the more rare my observations become. So that in a nutshell is how you kinesthetically generate the mean, the variance, and the standard deviation of a sample.